If you are interested in applied machine learning in the context of robotics, this is a tutorial for you. My name is Damian Bogunowicz and I represent The Arrival, where we shape the future of sustainable transport. As a part of this vision, my team is focused on shaping the future of intelligent industrial robots. This presentation is comprised out of two segments. The first, shorter one, is the presentation of our research in the domain of Sim2Real transfer. The second one is a tutorial on how to tackle the problem of robotic assembly tasks in the simulation using deep reinforcement learning. I will show you how to set up your environment, run the simulation, and finally use deep reinforcement learning to teach the robot how to do things. Before I start, I would like to give shout out to the robotics team at Arrival: Fedor, Sasha, Komal, Ivan, and Mikhail. It tends to be the norm that great things come from great collaborations, and our research is not the exception to this rule. So over the next few minutes, I would like to present our research. So this is the fruit of our work. What you see here is a neural network controller which takes only a single grayscale image as an input, as shown in the left lower corner, and is able to complete peg-in-hole insertion with 1 mm precision. What's really wonderful is the fact that this neural network was fully trained in simulation with no additional fine-tuning. Nevertheless, after transferring the model to the real robot, it does a very good job. So this is essentially the pipeline. First, we set up the environment in the simulation, then we train an agent, and those two steps will be covered in the tutorial, and finally we transfer the knowledge to the real robot. We are interested in flexible robots which can perform many various tasks. We are excited about end-to-end solutions because they reduce the effort of human design, and deep reinforcement learning seems to be the right choice. We also have access to practically infinite amounts of training data because we only train in the simulation. For more details, I encourage you to take a look at the paper we have published at the workshop at the recent ICRA conference. We have chosen peg-in-hole insertion because it's a good toy task which transfers well to more advanced assembly challenges. We are also convinced that vision from the eye-in-hand perspective is the most natural state representation for our task. We use Coppelia Sim Simulator as the environment and take advantage of Catalyst RL as our deep reinforcement learning framework. The robot in the image is UR5E equipped with a RealSense camera. We use 320 by 240 images with the optional auxiliary inputs such as depth maps or proprioception, which are robot joint angle information. We rely heavily on randomization of objects, so their colors and textures, as well as shadows and image augmentations. We use TD3 algorithm to make the robot output continuous actions in the 3D Cartesian coordinates. Our reward forces the robot to reduce the distance between the peg and the hole, while the act of insertion gives additional reward boosts. Optionally, we can punish collisions and add negative time reward, but those are optional blows and whistles. We are working actively to improve on our recent results. The improvements include, for example, endowing the robot with the sense of touch. We are also trying to combine reinforcement learning with pose estimation network or GANs. For instance, GANs helped us to map real camera image into simulation camera image so the model sees images in the same distribution with which it was trained on. Finally, we are also successfully tackling new assembly scenarios such as screwing. This concludes the first part of the presentation. Let's proceed to the tutorial. The goal of this tutorial is to show you how you can apply deep reinforcement learning to solve your own robotic challenges. For the sake of this tutorial, we have chosen one of the classic assembly tasks, pegging hole insertion. By the time you finish the tutorial, you will understand how to create a complete end-to-end pipeline for training the robot in the simulation using deep reinforcement learning. The code, together with all the details of the implementation, can be found in our GitHub repository. Let's take a look at the contents of the repository. It contains configs, which specify the RL algorithm and its hyperparameters. We have scripts, which are bash scripts meant to be run by the user to start training or inference. We also have the simulator scene in folder simulation. Those are TTT files specific for the Coppelia Sim simulator. Finally, we have the source folder, which contains all the interesting Python scripts. Before we start running any piece of code, we need to install Coppelia Sim from the official website as well as PyRep. PyRep library is built on top of Coppelia Sim to facilitate prototyping in Python. Although you can use Coppelia Sim on any platform, communication via PyRep is currently only supported on Linux. Finally, don't forget to activate the virtual environment using the provided requirements file. For our reinforcement learning project, we use Catalyst RL, a distributed framework for reproducible RL research. This is just one of the elements of the marvelous Catalyst project. Catalyst is a PyTorch ecosystem for deep learning research and development. It focuses on reproducibility, rapid experimentation, and code-base reuse. This means that the user can seamlessly run training loop with metrics, model checkpointing, advanced logging, and distributed training support without the boilerplate code. We strongly encourage you to get familiar with the intro to Catalyst and incorporating the Catalyst into your daily work. Let's run some imports. Alright. We reuse general Catalyst RL environment class to create our custom environment, Coppelia Sim and Wrapper. This class wraps around the general RL environment class to launch the Coppelia Sim with our custom scene. Alright. Okay, perfect. Additionally, in the beginning of every episode, it initializes randomly the physical properties of the mating part, so 2D position in the workspace, as well as the color of the mating part. We can print poses for each of the elements of the scene, the peg, mating part, as well as the camera. Note that the pose has 7 dimensions, 3 for position in the Cartesian coordinates and 4 for the quaternion rotation. We also print the color of the mating part and the table. The values are RGB normalized between 0 and 1. Let's run a sample control loop. We will move the peg downwards and then go upwards. For every step, we print the reward computed by the environment and display the grayscale image captured by the camera. In our RL framework, this will be the state of an agent. We can also try to simulate a successful insertion. The first while loop, right here, will align the peg in the plane of the table. So over x-axis, which is the 0th index of the pose vector, as well as over y-axis, which is the first index of the pose vector, right? So in the x-y plane. Then, in this while loop, we lower the end effector of the robot, so we apply action in the negative z-axis until it inserts into the hole. This episode terminates with the significant success reward in the final steps. Right? So here we have aligned, now we insert, and you can see we get reward, but at the end we'll get a massive reward because we'll sum the distance reward as well as the success reward for completing the task, and success reward is equal to 1. Alright. Finally, we can simulate a failed episode. We'll just lower the peg until it hits either the table or the upper face of the mating part. This will lead to termination of an episode without any additional reward. As you can see, no success reward here. Alright. So far, we have created an environment and specified how the agent can act and what the agent observes. But the intelligence of the robot is determined by the neural network. This brain of the robot is being trained using deep reinforcement learning. Depending on the modality of the input, the architecture of agent's brain changes. It could be a multi-layer perceptron if the robot learns solely from, for example, robot joint angles, or a convolutional neural network if it uses images, or both. Catalyst provides an easy way to configure an agent using a YAML file. This is the YAML file. Additionally, it provides implementations of state-of-the-art RL algorithms like PPO, DDPG, TD3, SAC, etc. One could pick the type of the algorithm by changing algorithm variable in the config file. So the algorithm variable can be found right here. The hyperparameters related to training can also be configured here. So as we can see here, many hyperparameters to choose and change and alter. TD3 uses two separate networks. Critic, right here, which estimates the value, goodness, of a state-action pair, as well as the actor. The actor decides which action the agent is going to take. During optimization, the updates of actor weights are directly influenced by the Q values estimated by the critic. The actor and critic, or critics in case of TD3, are modeled as agent classes in Catalyst. So as you can see, for our actor we have agent UR5 actor, and for critic we have agent UR5 state action critic. The CNN network, ImageNet, used to process camera images can be created as shown below. The layers of network are defined by number of channels, whether we use bias, whether we use group normalization, whether we use normalization, whether we use dropout, and which type of activation function we want to use. A MLP, in our example, either ActionNet or MainNet, are created in similar fashion right here. Training. So let's talk about the training process, which is fully governed by Catalyst RL ecosystem. We have sampler scripts, which explore the environment and collect the data. We also have a trainer, which uses the collected data to train a policy, both the trainer and samplers. And yes, you can have multiple samplers as if you had several different realities from which you collect experiences in parallel. So both the trainer and samplers are also configurable in the config file. The sampler starts with a random policy, and after a certain number of transitions, it updates its policy with the latest trainer weights. As the policy progresses, the sampler keeps on gathering data collected by better policies, while the trainer improves the policy until convergence. All the data is stored in a database. Once the parameters of trainer and sampler, and in the tutorial we use a single sampler, are configured, the training process can be started by launching the following bash script: scripts run training sh. This opens a Tmax session which starts sampler, trainer, database, and TensorBoard to monitor the training process. So, to wrap up, once you clone our repository, install CopeliaSim and PyRep and set up the virtual environment. Then you are ready to start training. Even though running the learning pipeline with the default settings almost guarantees that the training will converge, we encourage you to play with the parameters and alter the code to your liking and needs. The moment the training starts, the agent's progress can be also monitored visually in the CopeliaSim simulation. While training without any blows and whistles, if you are equipped with a single decent GPU, you should expect to see meaningful actions after roughly an hour. The training should converge in half a day. This is roughly equal to gathering an experience from 7,000 episodes. When you look at the training curve, you will notice that the robot quickly learns to approach the mating part. When reward starts exceeding the value of 0.8, those are the episodes where the agent managed to slide the peg into the hole. And this is roughly the point where the robot performs continuous full insertions. So as mentioned before, to train a robot, we need to launch scripts run training. We run in parallel 4 processes. First, the trainer starts. Now the sampler will start in a second. There you go. We can also see that MongoDB is running in the background, and we have also started TensorBoard. We can take a quick look. So it comes with different interesting metrics. What interests us the most as users is trajectory metrics and mainly reward. So reward is the most, I would say, direct measure of how the training of the robot improves over time. Another cool thing is the sampler will actually display the state of the robot during the training. So right now, as you can see, it tries some different random actions, but over time the peg will start approaching the mating part, and after some time it will start inserting continuously. Once this happens, we can run. So once this happens, we can start running Inference. To run Inference, first we have to modify the config file, the config inference file. And the important detail here is we need to pass as a resume variable the directory to our PTH file, right? So I have one sample PTH file right here, right? And now in the similar fashion to training, we just run scripts, run inference to infer this trained model. This model has been trained for some time, so it performs really nice continuous insertions. This concludes this talk. If you enjoyed this presentation, feel free to visit our code repository and go through the tutorial on your own. It's been an honor to participate in this conference and share our research with you.